Hello everyone, in this video I'll be talking about Network X, a Python library for creating, analyzing, and visualizing graphs. This is my submission for the Algorithm Analysis and Design course at Princess Sumaya University for Technology. Obviously throughout the course we have been studying graph algorithms like BFS, DFS, Dijkstra's algorithm, Prim's algorithm, so obviously we learned how they work. We trace them on paper, we analyze their time complexity, but a natural question is how do we actually use these algorithms in real code? How do we go from a graph drawn on paper to something running on a computer? Which is exactly what Network X is for. Network X is a free open source Python library that lets you build any kind of graph, run algorithms on it, visualize the results, in just a few lines of code. It's widely used in research, data science, and software engineering whenever graphs are involved. So in this video, I'll be showing you how to create graphs in Network X, how to visualize them, how to run the algorithms we've studied in class, including Dijkstra, BFS, DFS. And I'll be using Google Colab, which runs entirely in the browser, so there's nothing to install. So let's get right into it. Here I have a blank Google Colab notebook. The first thing I do need to do is go ahead and just import the libraries themselves, such as these. Just a second. Okay, so I'm importing Network X as NX. That's the graph library, and I import matplotlib for drawing and visualizing graphs. Obviously, both of these are pre-installed in Colab, so they work immediately with no setup. So let me create my first graph right now. Let me run the code though. Just a sec. Okay, perfect. Now to create my first graph, I'm gonna be, to save time, obviously, I'm gonna be explaining the code. So I create a graph object, store it in the variable called G, and add 5 nodes, numbered 1 through 5. Then I add edges between them. So node 1 connects to node 2, node 1 also connects to 3, 2 to 4, 3 to 4, and 4 to 5. In Network X, nodes can be numbers, strings, or anything really. Edges just represent the connection of the relationship between the two nodes. So this is an undirected graph, meaning the edges don't have direction. So if 1 connects to 2, 2 also connects to 1. Now let me go ahead and visualize it for you. Let me run it. And let me visualize it for you, which is the power of Network X. So I called nxDraw and pass in a few variables. I want labels to be shown on the nodes. I want a sky blue color, and I want the decent size so it's easy to read on the screen. And let me go ahead and run it. And there it is. You can see all 5 nodes and edges connecting them. This is essentially the same kind of graph that we draw on paper in class, but now it's generated from code. The layout is determined automatically by Network X using a spring layout algorithm which tries to space the nodes out nicely. Now this was a simple unweighted graph, but most of the interesting algorithms we've studied, like Dijkstra, work on weighted graphs. So let me create one of those for you. 1 second. So I create a second graph called G2. This time, instead of adding the edges from, I use add weighted edges from, as you can see. Each edge now has 3 values, the 2 nodes it connects, and the weight. And the weight can represent anything depending on the problem, distance between cities, cost of a connection, travel time, whatever makes sense for your use case, obviously. So here the edge between node 1 and 2 has weight 4, Between 1 and 3 is weight 2. Between 2 and 4 is weight 5. Between 3 and 4 is weight 1. And between 4 and 5 is weight 3. So let me go ahead and run it. And now I'm going to visualize the graph itself, the weighted graph. And I save the layout positions in a variable called POS. So the graph stays in the same position when I draw it again later. And I also pull the edge weights using this get edge attributes to display them on the edges. So let me go ahead and show you. So this is the title, weighted graph. This is to show it. Here is the weighted graph with all the weights visible on the edges. This is exactly the kind of graph that Dijkstra's algorithm, for example, works on. So let's actually run Dijkstra's on it. And the cool thing about Network X is that it has a built-in algorithm for Dijkstra's algorithm. As you can see here, it's I call it in. So obviously, I call Dijkstra path. I give it my graph, a source node, and a target node, and it returns the shortest path. And I can also call Dijkstra path length to get the total cost of that path. So let me go ahead and run it for you right now. Okay. So the shortest path from node 1 to node 5 is 1, 3, 4, 5. So let me just verify that manually. So from 1 to 3 is weight 2, 3 to 4 is weight 1, 4 to 5 is weight 3. That's 2 plus 1 plus 3, which is 6, correct? Now what about the other possible path? We could go from 1 to 2, 2 to 4, then 4 to 5. That would be 4 plus 5 plus 3, which would be 12, which is much more expensive. So obviously Dijkstra here correctly identified the cheaper route. And let me now highlight that path visually on the graph. Just allow me a second.
Everything correct so far? Perfect. Thank you for being a return customer. Let's leave information on a brief hold to reach out to the technician to let him know of this information. Okay?
So this is the shortest path highlighted in red. I colored the edges that are part of the shortest path red, and I leave the rest in black. And I use the same POS variable from before, so the graph layout stays consistent, basically. So let me show you. The red edges, as I said, show the route Dijkstra found, 1, 3, 3, 4, 4, 5. And you can see it completely avoids the 1 to 2, 2 to 4 path, because obviously it is much more expensive, and it is not the optimal path to basically take. Now, for example, for BFS and for DFS, let me show you. So let's run, for example, breadth first search on our first unweighted graph to remind you if it was this graph, starting from node 1. And BFS edges returns the edges in the exact order BFS traverses them. So BFS edges is a built-in functionality of Collab, and it's going to return the edges in the exact order that the BFS is going to be traversing them. So let me go ahead and show you that right now.
Edit and special instructions.
Okay, so BFS traversal order and edges is 1, 2, 1, 3, 2, 4, 4, 5. And obviously, as we studied in class, BFS explores all the neighbors at the current level before going any deeper. So it starts at node 1, and then it visits their direct neighbors 2 and 3. Then from there it visits 4, and then from there it finally visits 5. So 1, 2, 1, 3, 2, 4, 4,
Thank you
5.
for your patience.
And you can see that level by level order clearly in the output. Now let me just go ahead and compare that with DFS. And obviously it's depth first search, and it works differently. Instead of exploring level by level, it goes as deep as possible down one path before backtracking, trying another branch. So comparing the node visit order between BFS and DFS, BFS is 1, 2, 3, 4, 5, very level by level. DFS dives deep into one branch first before coming back, and that's the fundamental difference between the two. And now you can see it clearly in actual output rather than just tracing it on paper. So let me show
We're
you.
gonna see if it's possible to have the same technician that's being sent out today.
This is DFS order. We use DFS edges rather than DFS. We give it the source, which is the first node we want to start at, and we run it. And as you can see, it went from 1 to 2, 2 to 4, 4 to 3, then 4 to 5. So it visited 1, 2, 4, 3, 5.
Maybe provide you with that estimate if he's not.
So let me show you. So 1 to 2, 2 to 4, 4 to 5. And then it went, 1 to 2, 2 to 4, 4 to 3, and then 4 to 5. So it went the deepest it possibly could, hopped back up, and went even deeper with the node itself. And the nodes it visited were 1, 2, then 4, then 3, then 5. And that was because it ran deeper into 2 rather than visiting the direct neighbors of 1, if that makes sense. So basically, one last thing I do want to show is that Network X can instantaneously give you useful information about your graph, such as the number of nodes, number of edges, the degree of each node, which is how many edges it has, whether the graph is fully connected, meaning that you can reach every node from any starting point. And these are all things that we calculate by hand. Obviously, by pen and paper, you calculate it by hand. In Network X, it's just one line each. And for large graphs with thousands and thousands of nodes, this becomes incredibly valuable. So let me show you. So for an example, the number of nodes is 5, the number of edges is 5, the degree of each node for 1, it is 2, for 2 it is 2, for 3 it is 2, for 4 it is 3, and for 5 it is 1. Let me show you. So 5 nodes, 5 edges. For 1, the degree is 2, for 2, the degree is 2, 3, degree is 2, 4, the degree is 3, and 5, the degree is 1.
Thank you. That's not a special request.
And it is connected because, as you can see, if you started at 4, you can reach 1. Start at 2, you can reach 5. You can reach any point, starting from any point. So to wrap everything up, obviously Network X is a powerful Python library that makes working with graphs both practical and straightforward. In the video, obviously, we covered how to create both basic weighted graphs and weighted graphs, how to visualize them, how to run the three
Thank you for your patience.
the three searching basically algorithms from our course, which are Dijkstra's shortest path, the BFS and the DFS, and how to see the results directly. The library obviously has a lot more to offer beyond what I showed here, things like minimum spanning trees with prims and other algorithms such as crystals, centrality measures for analyzing networks, community detection, and much more. But what I covered today basically maps directly to what we have been studying in this course, and I do hope that it did give you a clear picture of how these algorithms actually look in practice. So please feel free to leave any sort of questions that you might have in the comments below, and I will do my best to answer. And one final thing I do want to show you, obviously, is from what we have showed here, is the fact that while
As of right now,
obviously in these examples it might not have been very efficient or very impressive to use collab, Network X. But for example, imagine if rather than having five nodes, you had maybe 500 and you wanted to see if the graph was connected. Now that would be where this would be a very practical tool to use and very useful. So yeah, that is pretty much on my end. If you have any sort of questions, any sort of use cases for Network X that you would like me to answer, basically, feel free to ask it down in the comments below. And yeah, I'll do my best to answer. Thank you so much for watching. It's been Ghaith Salameh, and I do hope you have a great day. Enjoy.